This is the 33rd lecture, the light has come. 33rd lecture, and we are going to discuss probability functions, various kinds of probability functions. In the last lecture, we had discussed the concept of discrete probability. Discrete probability, and we introduced several definitions. One was that if an event is multifaceted or if it is a composite event, then you talk of two probabilities, that is marginal. Marginal probability takes only one aspect at a time and does not consider any other characteristics of the event, whereas joint probability is the probability which considers both the aspects if the event has two aspects. As for example, in the example that we had cited yesterday, the color and the weight, if both are included, that is, you want a green ball weighing 3 grams, then it's a joint probability. On the other hand, if you want just a green ball, then the probability is marginal probability, P of, let's say, A, and we demonstrated by an example, demonstrated, not proved, Bayes' theorem, which says that the joint probability of two events or a composite event AB is given by another probability known as the conditional probability. Conditional probability has the significance that it is the probability of event A given that event B has already occurred. For example, you have already picked up a green ball. What is the probability that it is of weight 3 grams? Or you have already picked up a 3 grams ball. What is the probability that it is green? And then you multiply by probability, the marginal probability of B. And you can show that there is nothing sacred about A and B. We could have B with A has occurred and then the marginal probability of A. Now, these are fine as long as we are considering discrete events. For example, between green and red, there is no other color. All right. Our colors were, what were the colors? Red, black, white and green. Just the 4 colors. It was not a spectrum. It was just discrete lines. It is exactly like like a discrete time signal. It is not a continuous spectrum, and therefore we talked of discrete probability. There is a problem in going from discrete probability to continuous probability. It is continuous probability that we are more interested in, and the problem can be illustrated with the help of an example. From discrete probability to continuous probability. Well, let's say we have a box, we have a large box full of 1K resistors. Face value is 1K. You know that the face value 1K, if you make a precise measurement, you never get 1K. There is a tolerance, and the tolerance depends on how much money you are willing to spend on the resistor. If you spend, let's say, about 15 rupees, then you can get a thin film resistor with an accuracy of 0.0001%. On the other hand, if it is a 25 paisa resistor, the inaccuracy can be as large as 20%. In any case, you have a box which contains 1K resistors, all of the same size. What is the probability? The number of resistors is not specified. It's indefinitely large. A very large box of resistors, and all of them have a face value of 1K. Now, you know, if nominally it is 1K, depending on the tolerance, it could range from, let's say, 900 ohms to, let's say, 1100 ohms, okay? It could range from this. It could, because of tolerances, face value of 1K may measure as 900 ohms or 1100 ohms and anything in between. This is data that we know. Now, the question now, if we ask, what is the probability of picking up a 1K resistor? Obviously, between 900 and 1100, there are infinite number of possibilities. And therefore, if picking up 1K resistor is considered as a discrete event, the probability is 0, because the total number of possibilities is infinite. The value can range from 900 ohms to 1100 in a continuum, and therefore it does not make sense to talk of probability of picking up a 1K resistor. On the other hand, if we say what is the probability that the resistor lies between some range, let's say 995 to let's say 1005, all right, 0.5% tolerance, then this probability would be a non-zero probability. That means that if you want to go from discrete probability to continuous probability, a range has to be associated. That is, for continuous probability, you must define a range, and the usual manner in which range is specified is as follows. The probability that a variable, well, probability of let's say small x being a particular value of the variable which varies randomly, is defined as the probability. We'll amplify on this in a moment, but let me give the definition. It is defined as the probability is a continuous probability now. Small x is a continuum. It can range from some value, let's say a to b. For example, here 995 to 1005, and capital R is small x, all right. So what is the probability that a random variable, which is the resistor in this case, assumes a value of small x, not assumes a value of small x, but what is the probability that the random variable capital X, which assumes various values within a range, a particular value being small x, the definition is that the random variable should be less than or equal to small x. This is the definition of continuous probability, and we will elaborate on this in a moment. To be able to understand the conceptually the significance of continuous probability, we have to define we have already used the term, but we have to define a random variable. Perhaps these are concepts which you have not done before. You must have done discrete probability, may not be continuous probability. So I want your complete attention. Mostly in electrical engineering, in communications, in control, and in many other situations, what we are concerned with are random time functions. For example, noise is a random time function. A random time function is one whose value at any instant cannot be predicted. All right, this is the definition of a random time function. Let's say the function is x of t versus t. Well, it varies in a random manner like this, and its value at any instant cannot be predicted from its value at other instants. It cannot be predicted. It is not a regular functional form. It is a function of time, but the values cannot be predicted, and that is the definition of a random signal. Now, x of t could be just one member of a family of such time functions. For example, noise, if one records noise by various instruments at the same point, one may get different waveforms. All right. No, that is not a very good example. How should I do it? Okay, just take an abstract concept that we have a family of such xt's, a large number. All right, and each of them is different from any other. None of the members of the family are identical. If they are identical, we just call them one time function. So there is a large number of such time functions, and this family is then called a random process. A family of x of t's, each of which is a random time function, is called a random process. Now, a random process can be characterized by various kinds of parameters which you shall learn later, but for the present it suffices to say that a family of random time functions having some common characteristic is called a random process. What are these common characteristics we will see later. If in a random process is a family of x of t's. If in a random process the probability of a particular time function is also known, that is, if the family is known, the members of the family, let there be 100 of them, and what is the probability of observing one of them is known, of observing each of them is known, then this collection of random time functions is given a special name. It's called an ensemble, E-N-S-E-M-B-L-E. All ensembles are random processes, but all random processes are not ensembles. The difference is, random process is a collection or a family of random time functions. An ensemble is such a random process in which each member gets a number, which is the probability of occurrence of that particular time function. All right? You would understand the difference between a random process and ensemble. We shall also use the term sample function. Each of these members of a random process or an ensemble is called a sample function. So, the x of t that I have depicted here is a sample function. It is a member of the family and it is a sample function. All right. Now, let's concentrate our attention on one particular value of time. Let us say t equal to t1. Let us say somewhere here t equal to t1, and let this value, let this amplitude be called capital X 1, let us say. Capital X1 by definition is small x of t1 when I have confined attention to one sample function. All right. Now, if I observe, if there are parallel frames one after another, and all the 100 members or 200 members of the ensemble or the random process have been recorded. One of the examples is a seismological graph, seismic exploration. You get a series of such functions, shock wave functions as functions of time. These are all random. These are all random time functions, and they form an ensemble. All right. Let's go back here. You have an observer observing at the time instant t1, and he measures for the whole ensemble, he measures the values of x of x1. All right. Obviously, x1 shall be different from one member of the family to another. So, depending on the number of members in the family, if it is 100, he will get 100 values of x1. Obviously, x1 is a variable, right? It is a variable not over time. You must understand this. Small x of t is a variable, independent variable being small t. Capital X1, because you have frozen time is frozen at t1. Capital X1 varies over the ensemble. All right. Capital X1 varies from one random time function to another, and if you collect all of them, then capital X1 is a variable over the ensemble. The independent variable here is the designation of the family. For example, if there are 100, then x1 shall have 100 values. So, x1 is a variable, and this variation from one member of the family to another cannot be predicted either, because by definition the values of x of t at various instants of time cannot be predicted. So, capital X1 cannot be predicted, and capital X1 variation over the total ensemble cannot be predicted either. So, capital X1 is called a random variable. This is the definition of a random variable. All right. So we have defined a random process, we have defined an ensemble, the difference being that in an ensemble the probability of occurrence of one particular member or sample function is also known, and we have defined what is a random variable. Now, if you recall this diagram, let me show it again. Capital X1 obviously over the large number of members of the family, it could vary continuously. For example, capital X1, if it's a voltage waveform, could be 1 volt, could be 1.01 volt, could be 1.001 volt, and so on and so forth. That means capital X1 range could be a continuum. If it is a continuum, then it is called a CRV, that is a continuous random variable. On the other hand, if this is a digital signal, then obviously the value of capital X1, depending on the number of bits that you allow in the digital system, it can take some discrete values, that is one discrete value, one value from a countable set of specified values, and under that condition it is called a discrete random variable. Our attention shall be mostly with continuous random variables. You shall come across discrete random variables when you do the course on digital communication, or there is also an elective course on digital control which will be run in the 4th year. Now, so we can now give a definition, we can redefine or we can recall the definition of continuous probability P of x. This is defined as probability that a random variable capital X is less than or equal to small x. All right, random variable capital X is less than or equal to small x. Small x is a particular value of capital X, and the probability that the value of the random variable, no, P of x, this notation stands for probability that the random variable value is over a range which cannot exceed small x. It is not, P of x is not the probability that capital X is equal to x. No, because that does not make sense. In a continuous probability, that probability, if you define it that way, that will always be 0. Remember that 1K example, 1K resistor example. So this, do we assume a lower limit? Capital small x could be within a range, and this range could be minus infinity to plus infinity, or it could be a range from small a to small b. All right. So the range of small x can be unlimited or can be limited. All right. We will take examples of both later. But you notice that if x lies between minus infinity and plus infinity, if x lies between minus infinity and plus infinity, what should be the limits of Px? Obviously, no, probability cannot exceed unity, and it is a positive quantity. So it must lie between 0 and an impossible event. For example, if x lies between, let us say, 0.1 and 0.2, then P of 0.09 shall be equal to 0, right? And P of 2, can you tell me what this shall be? 1, because all values have been incorporated. Capital X less than equal to 2, all right. Now, therefore, it must lie between 0 and 1. Probability cannot exceed unity, all right. Number 2, if x increases within a range, any range, it does not matter, obviously P of x should be a monotonically, not necessarily increasing, monotonically non-decreasing function of x, all right, which means that P prime x must be greater than equal to 0. It is a non-decreasing, it cannot decrease, because you are increasing the range of x, so the probability shall most possibly increase. At the most it can remain static, at the most it can remain static. if there is an inflection point. That is, if you plot p of x versus x, there can be an inflection point where the slope is 0. It could be. Now, you also see that if x varies between minus infinity and plus infinity, then p of minus infinity is equal to 0. There cannot be a value of x less than minus infinity, and similarly p of plus infinity is equal to 1. All right. I have already said p of x, well, p prime x, this I have already said, yes, okay. The fourth property is that the probability that capital X lies between two limits, x1 and x2, obviously is p of x2 minus p of x1. Is this clear? The probability that the random variable lies between two limits x1 and x2 obviously is p of x2, which means capital X less than equal to x2, minus p of x1, capital X less than equal to x1. So, the total range is covered. Now then, what should we call this function p of x? What should we call this? Because it is a continuum, it is not a discrete event, small x is not a discrete event, and therefore, we must call it probability? No. It is called a probability distribution function, because p of x versus x is a continuous curve. The values of small x are continuum, so are the values of p of x. So, it is called a probability distribution function. A very appropriate. We do not call probability, continuous probability at a specific point. No, that does not mean anything. It is a distribution function, and the interpretation you have already seen, the random variable takes a value which is less than or equal to the argument p of x. And in our future discussion, we shall abbreviate this as capital P, capital D, capital F, probability distribution function. Probability distribution functions can be of various types, but whatever the type is, the slope must always be non-negative. It could also be 0, all right. And three such examples of probability distribution functions we will show. We can have, this is capital, this is small x, and these are capital P of x. All right, break the curve somewhere here. I am showing three examples. Now, we can have small x in the range minus infinity to plus infinity, unlimited small x. So, we can have a curve like this. What would be the uppermost value? 1. And the lowermost must be 0. All right. So, this is 0, and small x goes to infinity in this direction, minus infinity in the other direction. It could be something like this. It could be a finite range of variation. Instead of minus infinity to plus infinity, it could be something like this. Okay, that is possible, where this is a, and this, what would be this value? 1, and this is b. All right. This can be a possible plot where the range of x is limited. We could also have a plot like this. Let us say a staircase like this. All right, and that is the end of it. Now, one has to say, what is the value here? Again, 1. All right, and let these values be 0, a, small b, and let this value be small c. All right. In these three plots, the first two obviously are CRVs, isn't that right? They are continuous random variables. Whereas the next one, the third one, is the case of a discrete random variable. A discrete random variable can also be described by a probability distribution function. All right. In each of these, one has to remember that the slope is non-negative. The slope, that is capital P prime x, which is dp dx, is usually denoted by small p of x. Please distinguish between small p and capital P, because we shall use both. The slope is usually denoted by small p of x and is called the probability density function. Now comes the question of density. And in practice, the probability density function is more important and more useful than the probability distribution function. To denote probability density function and to distinguish it from probability distribution function, we write probability density function with lower capitals, that is small, what are these called? Small letters, small case letters, lower case letters. Okay. Small p, small d, small f. The other one is capital P, capital D, capital F. This is called probability distribution function and this probability density function. Now, as I said, in practice, probability density function is more important and more useful than probability distribution function. But before we go to an interpretation, a physical interpretation of the probability density function, let us see what the density function shall look like in these three cases. We had one of the curves was like this, second one was like this with a point of inflection, and the third one was like this. The upper limit in each case is 1, 1, 1. And this goes from minus infinity to plus infinity, a to b, and this is 0, a, b and c. Let us see what the probability density function shall look like. Okay. Obviously, in this case, the maximum slope is here, and the slope at infinity, plus infinity and minus infinity both at 0, and therefore it would be a bell-shaped curve like this. All right. It has a peak at x equal to 0. This coordinate, this ordinate abscissa is x, small x. In this case, there is a 0 slope here. All right. So, and the slopes are maximum here, and therefore the function shall be like this. This is A and this is B. This is a probability density function. In this case, what shall be the shape? Obviously, impulses, right? So, there will be an impulse here at 0, depending on the height. The strength of the impulse shall be defined by the height. So, we shall have an impulse at A, we shall have an impulse at B, and we shall have an impulse at C. 0, A, B, C. The slope is an impulse whose strength is determined by the jump that occurs at that point. So, a discrete probability density function shall consist only of impulses, and this picture will clearly show whether the original variable was a continuous random variable or a discrete random variable. Now, let us come to the interpretation of the probability density function, small p, small d, small f, small p of x, which is equal to p prime x. Now, if you recall the definition of p prime x, it is p of x plus dx minus p of x divided by dx, where dx, I should have used something else, delta x tends to 0. All right, let us keep it as dx. Then you notice, is implied that dx is an infinitesimal quantity. Then you notice that p of x dx is simply the probability of x plus dx minus probability of x, which means that it is the probability that the random variable x lies between x and x plus dx. This is the interpretation. Alright, it's the other way around, correct. That is correct. This is the interpretation. Small p of x is the probability density function, and small px multiplied by dx is an element of probability, or a probability element. P of x, small px dx is a probability element which indicates the probability that the random variable lies between small x and small x plus dx. This is the interpretation of probability density function. Obviously, probability density function does not, it has to be non-negative. So, it is greater than or equal to 0. But is there an upper limit on this? No. We have already drawn a picture where it goes to infinity. So, the value of p of x is not restricted, the upper limit is not restricted, the lower limit is restricted to be equal to 0. Alright. So, if we summarize the properties, p of x is greater than or equal to 0, minus infinity, less than or equal to x, less than or equal to plus infinity. What is the integral from minus infinity to infinity? Small px dx. This is equal to 1. Why is it 1? Can you prove this?
So, because the total probability has to be 1.
No, I want in mathematical language.
So P infinity and P minus infinity.
This is capital P infinity minus capital P of minus infinity, which is, this is 0 and this is 1, and therefore it is 1. Alright. Third, the probability distribution function, capital P of x, is related to probability density function by an integral. P of x is capital P prime x. So, capital P of x must be the integral of small p of x. In other words, pu du. Can you tell me the limits?
Minus infinity to u.
Minus infinity to x. That is correct. Alright. And if I integrate small p of x, small p of u du from x1 to x2, what does this indicate?
Px2 minus px1.
That is correct. Obviously, it is px2 minus px1, but this is the probability that the random variable lies between x1 and x2. Now, some of the probability density functions which you shall encounter in future in your future courses, I would like to list them. One is the most usual probability density function that you get is Gaussian. Name of this is density function, not distribution. And pardon me?
The first type.
First type?
Bell shape.
The bell shape. That is correct. And the mathematical expression is, you must remember these constants. These constants have a very special significance. Square root of 2 pi sigma e to the minus x bar squared divided by 2 sigma squared. This is the Gaussian distribution, and the range is minus infinity to plus infinity. A couple of comments about the nature of the distribution. You see, there is a constant 1 by square root 2 pi sigma, and then the power of the exponential is not x, is neither x squared, it is variance, it is variation of x or distance of x from a certain fixed point x bar. We shall know the interpretation of x bar and sigma later. X bar is the so-called ensemble average. It is not a time average. X bar is ensemble average. Sigma is the variance. Is sigma the variance or sigma squared the variance? Sigma is called the variance. Sigma squared is called standard deviation. All right. And the interpretation or the significance of this constant is that integrals from minus infinity to plus infinity should be equal to 1. All right. This is the most usual distribution that you will encounter in practice. Then there is a distribution due to Rayleigh, the same Rayleigh as who wrote the book on acoustics, Rayleigh from acoustics, and his distribution, his density function was x by eta squared e to the minus x squared divided by 2 eta squared. Eta is a constant. The eta is a constant. The only criterion is that the integral should be 1. Now what can be the range? Can x be from minus infinity to plus infinity? No, because there is a minus x squared. Is that the reason?
No, sir. The x square.
This x. Alright. So Rayleigh distribution is limited to 0 less than equal to x less than infinity. Then of course there is a simple exponential, not distribution, this is a density function. I am making a mistake. It is the density function. Exponential density function is alpha e to the minus alpha x. Alpha arbitrary, and once again the limit is 0 less than equal to x less than infinity. What is the problem if I make x minus infinity? It will blow. Alright. And then the simplest distribution, simplest density function is the uniform density function. That is, between some range x1 to x2, it is uniform. Can you tell me what the height shall be?
1 by x2 minus x1.
That is correct. This is to make the area equal to unity. So this would be 1 by x2 minus x1. This is the uniform distribution. In most of the discussions on, let's say, when you talk about digital signal processing or digital communication, it is very convenient to assume a uniform distribution as a constant. And many a times we do this. But there are hardly any random processes in which the distribution can be uniform. It is almost impossible to have a uniform distribution. The closer to nature, closer to natural distribution is the Gaussian distribution. And its Gaussian is sometimes also called the natural distribution. But I can tell you all practical processes deviate from any of these mathematical descriptions. They defy all such mathematical descriptions. We adapt one or the other depending on what we are more concerned with. Are we concerned with a quick result, an estimate, or are we concerned with very accurate results, and so on. Next we introduce the concept of mean values and moments. Now if we have a random process, let's say x of t, incidentally I have not told you the symbol for a random process. X of t is a random time function, RTF, alright. If we enclose x of t within curly brackets, this will denote a random process, alright. If we enclose x of t within curly brackets and include in this the probability of each member that is xit, then this is an ensemble. Alright. This is the notation. Now consider a random process. If we take the time average over any member of the family, obviously because it is random, the time average is likely to be 0. And it doesn't make sense to take time average, because in any case you cannot predict the function. On the other hand, if we take the ensemble average, that is the value of a random variable, the average value of a random variable over the complete ensemble, then that will make sense. That will describe, that will be a parameter of the random process, and it can be used to characterize a particular random process. And obviously if we have to take average over an ensemble, then this average must include the measure of probability all right, it must include a measure of probability, and this is why the probability density function is more important than the probability distribution function. That is, what we do is we take x, then we multiply by the probability that the random variable assumes a value between small x and small x plus dx. That is, we define the probability element x px dx, and then we integrate from minus infinity to plus infinity and divide by minus infinity to infinity small px dx. This average makes sense, and this average is the so-called mean value or the average value of average value of the random variable, average value of the random variable. It is also the average value of the random process, because capital X1, you recall, we froze time and we said capital X1 is x of t1, and then we went over the ensemble, we kept on measuring and so on. Now, the average value of this random variable, there is no reason why it should not be the same as the average value of any other random variable, all right, time being frozen at some other instant t2. So, in that sense, x bar also is a parameter of the random process. In a similar manner, what is this? The lower
1.
integral is 1, and therefore x bar is simply given by this. In a similar manner, any function of the random variable f of x, I can take the average value as minus infinity to infinity f of x px dx. This is called the average value or the mean value. This average is not over time, I repeat, it is averaging over ensemble, and it is called an ensemble average, or more familiar terms to mathematicians and statisticians is the expected value of capital X, the random variable. The statisticians use the term expected value, or it is also sometimes called expectation of x, and sometimes we write this as E of x. E of x is this E is an operator, it is not a functional form, it is an operator operating on x, gives you x bar. In a similar manner, if expectation operator operates on fx, then we get f of x bar. This bar is over the ensemble, and one of the very important cases of f of x is x to the power n. Suppose f of x is x to the power n, then E of x to the power n, where n is an integer, which is equal to x to the power n bar, is given by minus infinity to infinity x to the n p of x dx. Obviously, for n equal to 1, it is the mean value. For n equal to 2, x squared, it is x squared bar. What can you say? What? Mean squared. Mean squared value of the random variable small x, and it is not necessarily equal to mean value squared. Mean value squared, you must distinguish between them. Mean squared value is x squared bar, and mean value squared is x bar squared. This is mean value squared. Mean value squared. There are processes in which the time average, for example, a sinusoidal signal corrupted with noise. The time average, if a sinusoidal signal is corrupted with noise, then the whole signal can be considered as random. Isn't it right? But the average value of this, the noise part, the average value, time average is 0. But the sinusoidal signal, the time average is not 0. You can find therefore the average value is the average.
Why is it not 0? It is 0.
the average is defined over a period. Average value of a sinusoidal signal, how do you define? Obviously over, no, it's not over one period. Over one period again it's 0. It's over half a period. All right. So the average value there makes sense, and the mean squared value in such instances, have I told you the instance in which the time average is the same as the ensemble average? All right. If you are sending a sinusoidal signal which is corrupted by noise, you have an ensemble, and you take the ensemble average and you take the mean squared value, they are equal. There are processes in which they are equal. If they are equal, then obviously mean squared value is proportional to the power in the signal. In general, it is not. I have just mentioned an exception. In general, mean squared value of a random process or an ensemble has nothing to do with power. This mean squared value is averaging over the ensemble. It is not averaging over time, and this must be remembered. Finally, we define what is known as a central moment. Central moment, abbreviated as CM. The nth central moment is abbreviated as CMN. Nth central moment is defined as the expected value of the distance between x and its mean value, x bar, to the power n. That's what it is. In other words, it is the average value of x minus x bar to the n, average value of this. All right. Obviously then, CMN is equal to integral minus infinity to infinity x minus x bar whole to the power n p of x dx. This is the central moment. Now, what is the reason for the use central? Central because x bar is considered as the pivot, and the distances are measured from x bar, not from the origin. This in the previous case, the mean values, they are also moments. For example, x to the n bar is integral x to the n px dx. Here distances are measured with the origin as the pivot. Here distances are measured from x bar or the mean value. If you go to, I am sure you have studied momentum inertia, there is something called a radius of gyration. All right, distances are measured from the center of gravity, and it is in that sense that center comes. X bar is considered as the center, and therefore this moment is called the central moment. It is all from a similarity with momentum inertia, radius of gyration and so on. Otherwise the term moment does not have any other significance. All you have to remember is the definition of the central moment. Now obviously, if n equal to 1, then what is Cm? It is 0. If n equal to 2, that is expected value Cm2, expected value of x minus x bar whole squared, this we can write as x squared minus twice x bar plus x bar squared. Expectation operator is an integration operator, and therefore expectation is a linear operation, and therefore you can write this as e of x squared minus twice. X bar is a constant, so its expectation is x bar itself, x bar, then expectation of x plus x bar squared. And you notice that this is x squared bar minus, what do you have? Twice x bar squared plus x bar squared, and therefore this is equal to x squared bar minus x bar squared. You understand the need for distinguishing between x bar squared and x squared bar, all right? This is called the central moment 2, and the name for this is, well, it is denoted by sigma squared, where sigma squared is called standard deviation. Well, sigma squared is called variance, not sigma. Alright, sigma squared itself is called variance or standard deviation, whatever you want to call it. Or is it that the standard deviation is the square? Yeah, sigma is called the standard deviation. Sigma squared is called the variance. Alright, we will start from here next time.